What I really want to do this week, as I said, is solidify the idea of linear vector spaces and Fourier series as an example. We're going to focus on Fourier series, but we're also going to do Fourier transforms. The other thing I want to really focus on is I really think if we treat these as expansions with a basis and a linear vector space with a defined inner or scalar product or dot product. So now I think I actually may have not used this word yet in the lectures. Inner product is the same as scalar product is the same as dot product. With these defined, we're going to do two things. I'm hopefully going to develop a better intuition for you of Fourier series, as well as really finalize these linear vector space ideas. Just as a reminder to me, who has done Fourier series before? I think it was a few of you. Excellent. Now, the thing to keep in mind, this is one place where I essentially do not follow the book at all. I will get all the same answers as the book, but I'm doing it from a very different perspective than the book. I think this is incredibly useful in this one case. So you will want to read through the book, and you will want to compare the two. I will point out the key main difference in my results from the book's result, which is not really a difference at all. It just looks like a difference. It's very useful because you will pick up for a series, for a transform books for the rest of your career if you stay in science. And there are a lot of conventions that are used differently, whether it's an engineering book, whether it's electrical engineering, whether it's a fluid mechanics book, whether it's a physics book, whether you're doing time domain or whether you're doing space domain, whether you're doing it in a Mathematica, MATLAB, or some C package. So the conventions around it really vary. It can be confusing, and you can actually get things wrong. And I think the best way to understand where all those conventions came from is actually doing it from this linear vector space perspective. What does that mean? We have to kind of develop a few key ideas. And the biggest one is to get used to the ideas as functions as a linear vector space with an inner product. And the other useful thing about doing it this way is that once I've done this for Fourier series, I can now do this. You're going to expand things in spherical harmonics in E&M. You're going to expand things in Chebyshev polynomials. You're going to expand things in Hermite polynomials. You're going to expand things in Bessel functions expansion. Any expansion in functions follows the exact same procedure we're going to do now for Fourier series. It is no different. You just take the word Fourier and do a find and replace with your new function name. The only thing that can be different is occasionally the inner product is defined in a slightly different way. And if you know how your inner product is defined, then everything we do works. And if you write it as bras and kets, then it all happens without worrying about this until the last step. So that's one of the real powers of this. And that's going to happen in E&M a lot. It's going to happen in quantum mechanics a lot, these different expansions. So it's very powerful. If we're going to do this, if we're going to take functions as a linear vector space, one is we have to recognize we're now dealing with infinite vector spaces. Why, do you think? Let me put it this way. One of the first things we need, of course, is our domain. What is our function acting over? Let's suppose I want to start with the simplest thing. Functions defined from minus a to a over all real numbers. If I want to define my function for you and tell you what my function is, in principle, what do I have to do?
Tell you what it is on every single point.
I got to tell you what the function is at every single point. The natural basis is the points of the real number, real number line, right? So the natural basis are the points from minus a to a. How many are there? How many real numbers are there between minus a and a? An infinite. And so my basis is infinite, so my dimension is infinite. Now, if you want to be fancy, this means we're using the delta function x minus a as our basis. We're not going to do that much in the class now. We may come back to it. This is the other delta function, the Dirac delta function. This is, for now, consider this cultural information. Okay? Now, but this is the key thing. Now, to make it a vector space, we already found that we have to worry about what? Once we know its domain, what do we need to know? What was kind of like the key thing when we were doing those quizzes on Thursday, when we were talking about the linear functions or all functions defined from minus a to a or 0 to a? What did I need to know about the endpoints? I needed to make sure when I added my functions, I stayed in my vector space. So the boundary conditions really mattered. And there's a couple that work pretty well. There was what we called periodic. There was also if they just equaled 0. And those are the two most common for finite ones. The other big one is to have f of x go to 0 as x goes to plus or minus infinity, and have the integral of the square of x dx from minus infinity to infinity be less than infinity, meaning it's defined. And this is what we call square integrable functions. So the function itself might diverge, but if I square it, then that integral converges. And why do you think what matters that the square converges?
Like alternating functions?
Well, that helps with alternating functions, but
inner products with themselves, functions with inner products with functions of themselves, you get the square.
right. When we remember integration, we mentioned briefly last week, is going to be the inner product, and we're going to do that in more detail. And so you want the inner product to be defined. You're never really integrating just the function itself. You don't really care what it does. What you care about is the inner product. Now, the domain, the boundary conditions. The next piece we're going to want to talk about is a basis. So I've done this twice already, but let's do it again. We have a basis. We call that basis n, which are the polynomials x to n. We know we can write any function using our Taylor series. Well, not any function, but almost any function. Where a sub n is defined to be the nth derivative evaluated at 0 over n factorial. And this is where the idea of a basis being linearly independent versus worrying about it being orthogonal is key. There is absolutely nothing wrong with this as a basis, and there's nothing wrong with it as an expansion. But we'll see it doesn't make the most sense as an orthogonal expansion. Now, if we want an idea for an inner product, then what we're thinking about is defining the length or the norm of a function and the idea of orthogonal. And remember, fundamentally, f of x is perpendicular to g of x if the projection of f of x onto g of x equals 0. So if I want to think about those two features of the inner product, what would be, when it comes to functions, a natural way to define my inner product? Talk to the person next to you about this. Think about all the things you could do to a function. what are some action you could do to a function that would kind of give you a natural intuitive idea of how big the function is over the whole domain you're looking at, and a natural idea of whether that function would project onto another function. Talk to the person next to you about that. So what are some things we could do? What are things we can do to a function? Just list some things you can do to a function. You can do what? What? No. Just what you actually do with functions.
Integrate.
You can integrate it. What else can you do to a function? You can take the derivative of it. What else can you do to a function?
Evaluate it.
You can evaluate it at each point. What else can you do to a function? Add it to another function, right? What else can you do to a function? Like if I had two functions, what can I do to the two of them?
Multiply them.
I can multiply them together, right? So what might be something, first of all, we have to get a single number out, right? The idea is the inner product must give us a single scalar number. What of all those actions we just talked about is the one that gives us a single scalar number? The definite integral. It's the only thing that does. Now, what is the integral, let's just say we're on a finite range, from minus 8a of f of x dx? We use a phrase when we first teach calculus. It is the what?
The area.
The area under the curve. Now, is this a good start? Do you think this might make a nice definition of the magnitude? Yes, no, maybe.
Yes.
Well, what's the problem with this as a definition for magnitude?
Because when you do the negative, it's going to subtract away your jump.
First of all, it can be negative itself.
The zero function should only be the one that evaluates.
So 0 is the only one we want to evaluate explicitly to 0, hopefully. So what would be a better way to get how big this function is? Square it. And so that would tell us, right, that this function, versus this function, they're about the same size because they both have similar area under them. So we would like this to be squared. This suggests a definition of inner product to us. Now let's ask ourselves, does this definition of inner product make sense for the idea of a projection? Because that's going to tell me if I project g onto f, I'm going to integrate f, and I'm going to put a complex conjugate there because I know that my inner product, when I switch it, gets a complex conjugate. So fg, this is my rule of defining an inner product. If you recall, fg has to equal gf complex conjugate. So if I say the one on the left is complex conjugated, the bra, which we've done a lot, gets the complex conjugate. If I switch them, the integral of f star g is the complex conjugate of the integral g star f. And you can prove that because it's a linear operation. So it doesn't matter. So if I do this, do you think this will give me a sense of projection? What is this really, physically and intuitively? We don't spend enough time thinking about integrals intuitively. What does it mean when I integrate the product of two functions? Or another way to say it, suppose that's f and that's g. What am I going to get? Really? When I multiply those two? I'm going to get darn close to 0, and if these actually go to 0, I'm going to get 0, right? Because g is 0 over here, f times 0 is 0, f is 0 over here, g times 0 is 0. So do these two functions overlap?
No.
Do you expect there to be any projection then?
No.
And would the integral of f star g give me 0? And as I start sliding f over g, am I slowly going to get bigger and bigger and bigger?
Yes.
And where will the maximum be? When they line up on top of each other. So intuitively, and this type of integral, two functions multiplied by each other, comes up all the time. We use it for correlations, convolutions. We are constantly trying to measure behavior in physics by multiplying two functions and integrating over that. It is a common structure that we're going to use. And intuitively, it's about, do they overlap? And that's what a projection is. So this definition of the inner product gives us all of the physical intuition we want for an inner product, as well as matching all the formal rules of an inner product. It's got to give us a scalar. It's got to be linear in f and g. Integration is linear. It's got to have the complex conjugate when I switch them. Putting that there has the complex conjugate when I switch them. So this is our definition of inner product. And when we do that, we realize, okay, the integral from let's just do even more arbitrary. Any integral a to b of x to the n, x to the m dx. Okay, testing your math ability. What is this integral?
X to the
Yeah, so do the whole integral. Let's do it.
plus n minus 1 over.
No, I wouldn't do minus 1.
Plus 1.
Yeah, because we're integrating.
Right, over n plus 1.
From what?
From a to b.
And does this equal 0?
It depends.
Well, when would it only equal 0 in general?
When one of them equals 0.
If both of these are 0,
Yes.
right? Or if this happens to be odd, and you get lucky, right? If n plus m plus 1 is odd, and you have the exact right a and b, you might have intervals where these are orthogonal. But in general, is this orthogonal?
No.
No. So it's not generally orthogonal. So now the question is, where do we find our orthogonal basis vectors? And what's going to happen, the big idea is, and this is going to bring together everything we've been doing the last 2 weeks, is we're going to use Hermitian operators. Because, does anyone remember what the eigenvectors of a Hermitian operator are? Orthogonal. So if I know how to define an operator in my vector space of functions that's Hermitian, and I can find its eigenvectors, I now have a basis that's orthogonal. And all of the what we call special functions in physics that are useful because they're eigenvectors of Hermitian operators. So everything that we do, all of these things with special names, spherical harmonics, Hermite polynomials, Bessel functions, Chebyshev polynomials, sines and cosines, they're all useful because they're eigenvectors of Hermitian operators. And that's kind of like the big idea that's going to bring this together.